Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Tonight's guest is Paul Steinhardt, the Albert Einstein Professor in Science and Director of the Princeton Center for Theoretical Science at Princeton University, where he's also on the faculty of both the Department of Physics and the Department of Astrophysical Sciences. Dr. Steinhardt is a genuine Renaissance man in theoretical physics. Where most physicists of his stature have very narrow specializations, he has made major contributions to particle physics, cosmology, and condensed matter physics. And across all endeavors, he's been amazingly productive. He holds a number of patents, and he's authored hundreds of professional articles and 3 technical books. He's also written popular articles and co-authored with his colleague Neil Turok one popular book on cosmology, Endless Universe, which he'll discuss tonight. Dr. Steinhardt has many distinctions and awards, only a few of which we can mention here. He's a fellow in the American Physical Society and a member of the National Academy of Sciences. He shared the Dirac Medal from the International Center for Theoretical Physics in 2002 for his contribution to the development of the inflationary model of the universe. The Oliver Buckley Prize of the American Physical Society in 2010 for his contribution to the theory of quasicrystals, and the John Scott Award in 2012 for developing the theory of quasicrystals and discovering the first natural quasicrystals. Dr. Steinhardt is probably best known to a wider public for 4 things: his contribution to the inflationary model that's part of the Big Bang Theory now, his introduction of the concept of quintessence, the dark energy associated with the acceleration of the universe, the cyclic model in cosmology developed with Neil Turok, and the theoretical development with Dov Levine of the quasicrystal and his subsequent discovery of authentic examples of this improbable entity. Tonight, Dr. Steinhardt will talk about 2 of his great contributions: the concept of the cyclic universe and how that conjecture has evolved, and his work on the improbable quasicrystal, which he predicted theoretically and then ultimately tracked down. Despite his fame and the endless demands on his time, Dr. Steinhardt is much concerned to make exciting but challenging areas of science accessible to the general public. That's why he's joining us tonight. We are deeply grateful and very, very honored to welcome him tonight to Contemporary Science. Welcome.
Well, thanks, Yvonne. It's a pleasure to be here. Thanks for that kind introduction.
All right. Then you're left with explaining everything. And
Okay.
this is a tall order here.
Okay.
We are going to first talk about the cyclic model that you developed. And so to get to that, we're going to backtrack, right?
Okay.
And talk, if you'll refresh our memories, about the Big Bang, and then we'll go to the inflation and so forth. So tell us what happened. It's easy.
Oh, okay, sure. Well, our ideas about the universe have been evolving over the course of a century. Beginning about 50 years ago, we converged on what we call the Big Bang model. The basic idea there is simply that the universe that we observe today, the patch of space we observe today, once occupied a very tiny region of space and was filled with a hot fireball of radiation, gas, matter, and it's been expanding and cooling over the last 14 billion years, gradually forming more and more complex structure, beginning with the first nuclei, the first atoms. Around that time, the universe became transparent, then became the formation of galaxies and stars, and most recently, about 5 billion years ago, a new form of energy took over the universe, maybe quintessence or a form of dark energy that's caused the expansion of the universe to accelerate. So that's the basic Big Bang picture.
Okay. Now, apparently, we always talk about the first 3 minutes of the origin of the universe, out of practically nothing or nothing and into something, but there was this extraordinary first second, apparently, or much, much less, that is the part that's been very difficult, apparently, to reconstruct. Is that it?
Yes, it's been crucial. All the important features of our universe, all the large-scale structure, all its properties in the formation of galaxies were all seeded by events that occurred in the first fractions of a second. Maybe not even the first second, maybe the first billionth of a second, or maybe even before the Big Bang. And that's part of the issue we're going to be talking about tonight. So in the conventional Big Bang picture, the assumption has been that the Big Bang is a beginning. There is no space and time before. And so the only choice for making the structure in the universe or explaining anything about the universe is to imagine it occurred within that first second, within a first fraction of that second. And that's what led to an idea that's called inflation. Without inflation, if the universe were just to suddenly emerge from the Big Bang, it would be very uneven, non-uniform, turbulent, and space itself can be curved and warped. Yet when we look out at the universe, we don't see that. We see that the universe is extremely uniform on large scales. So we need some event to explain that. And the concept was that if the universe underwent a period of extraordinarily rapid expansion, accelerated expansion, that would stretch it so fast that the matter couldn't even keep up with it and the radiation couldn't keep up with it, it would stretch space glassy smooth. And any curvature that was in the universe or warping would be flattened out. And that's like an ironing board or stretching a rubber sheet would flatten something out. And this would explain these features of the universe. Then when inflation ends, it doesn't end in a smooth way. It ends in a way which is somewhat random, driven by quantum processes, much like what causes atoms to decay. So some regions of space would decay before others. And so you would be left, although you were glassy smooth at first, there's a slight wrinkling to the distribution of matter and radiation left over. And that's another feature of the theory. This tiny wrinkling would form the seeds that would eventually form the galaxies and all the structure we see today.
And that's the stuff you'll be showing us with the Planck and with the W.
This is what we try to prove. This is what
exactly,
right. With the data.
Right. Now, this inflation has been a very confusing idea. I don't know if it's as confusing to physicists and cosmologists as it is to the general public, but it's very hard to imagine, first of all, this happening in such an incredibly minute amount of time, almost non-time, but to come up with that, as Guth did, the inflation idea, you were instrumental in actually working on that because many people worked on it, but he credited you in particular for that. So you helped to solve some of the issues. Can you tell us a little bit, like, what's the issue? And
the issue, in Guth's original formulation, he figured out how to get the smoothing by this rapid stretching, but he couldn't get it to end. So the question was, is there any way to get it to end so that when you're done, the universe looks like what we observe it today, full of matter and radiation, and so it can form stars. So my student, Andy Albrecht, and I, along with independently a Russian named Andrei Linde, came up with the first examples where you could not only just have your inflation, but it would also undergo what we call a graceful exit to a universe that would look like what our universe was supposed to have looked like in its early stages to explain the structure we observe today.
Okay, so you were instrumental in developing that part. Now, can you tell us anything about how you became disaffected with this and moved to the development of the cyclic model?
Sure. Well, it was a combination of two things. It wasn't first disaffection. It was first simply asking the question, is this the only way of explaining the structure we see? So part of it was that curiosity. But then as we began to understand inflation better, a serious disease emerged, a serious flaw emerged that we're still dealing with today. And that is that although I told you that inflation comes to an end in our ideas, it actually doesn't come to an end. It comes to end in certain patches of space, but most of space keeps inflating away. And the reason why this happens is because of the same quantum fluctuations that are producing the wrinkles that we're seeing will occasionally produce regions of space which don't inflate which do not end inflation when they were supposed to. They stay inflating. And although they seem rare and it seems like you could ignore them at first, they can't be ignored because they're inflating. So within a matter of instants, they occupy more space in the region than the normal region, what you would have said was the normal region of space. Now, the process continues. The part that's inflating again tries to end inflation. Again, it fails, but leaving another patch, and another patch, and another patch, producing patches, an infinite number of patches over time. The real problem is that these patches are not all alike. Again, due to the rare quantum effects, an infinite number of them might be like us, but an infinite number of them would not be like us. Every prediction that inflation was supposed to make and supposed to be famous for, there would be an infinite number of regions which it would not be true. So the theory broke down, developed this disease that it produced what we call a multiverse. Not a universe that's everywhere the same, but a multiverse in which anything that you could conceivably imagine happening would happen an infinite number of times. Such a theory has no predictive value. That's the problem. And so one had to ask the question, is there a way of curing that, or do we need to seek an alternative? And so the cyclic model came out of an attempt to develop an alternative.
Okay, so could you tell us about the cyclic model here, how you came to that and how that developed? That's quite a story,
Sure. Well, we just said that the inflation idea seems to have failed. It seems the theory seems to have developed a disease, an incurable disease, and it produces this multiverse. So if something like that fails, you have to give up one of the assumptions that led to that theory. And all we assumed was the Big Bang was a beginning and it became hot and expanding. So the idea of the cyclic model was to give up the key assumption that the Big Bang is a beginning and imagine instead that it's a bounce, a transition from a phase that existed before, bounced, let's say a contracting phase that existed before, bounced and became an expanding phase. When you allow that possibility, suddenly you have new possibilities for smoothing the universe, flattening the universe, that you don't have to do it in a fraction of a second. You have lots of time before the bang, so to speak, or before the bounce to accomplish it. And what we developed was a theory for exactly how that would happen, how you could smooth and flatten the universe not during a period of rapid expansion, but during a period of very slow contraction. And then when the universe bounced, it would already, after the bang, already have all the features that inflation was supposed to produce in that first fraction of a second. But it wouldn't have this multiverse problem. And the reason why it wouldn't have the multiverse problem is because the reason why it happened in inflation is because rare regions left behind were getting expanded so rapidly that they would end up taking over the volume of the universe. In a contracting universe, you would also have rare regions left behind, but they're contracting. So they never occupy much volume. They disappear while regions that bounce begin expanding. So you don't have this competition between the rare regions and the typical, and the regions you meant to be typical. So it produces a universe in which everything is nearly the same, rather than a multiverse in which anything is possible an infinite number of times.
I'd like to get a clarification for one thing here. First, go back to that inflation. In the typical story for the inflation, this is a brief period that just makes this expansion faster than anything we can imagine. But we don't usually hear, well, it goes on forever. The universe expands forever, but it's this inflation and highly irregular inflation is something that is less familiar. I just wanted to get that
it's eternal.
clear.
So in fact, we call this eternal inflation. That although there are patches where it ends, and we'd be one of those patches, we'd be a rare region. We would be very rare, atypical regions of space. Most regions of space would keep inflating. And even when the patches which have stopped inflating, those rare patches, we would also not be typical. There'd be, anything would be possible.
I see.
That's why there's this problem with deriving predictions from such a theory.
Because it just, would become unprovable and everything else. Then I'd like to go back here to bounce. Now, one of the things that gets confusing with bounce is, you clearly had some kind of a beginning because we only had nuclei. You had to have a cooling period to get to the nuclei, and then you have a long period before we can have atomic structure and so on. In the bounce, do you start at the similar beginning like this minus the inflation?
Yeah, so you begin, after every
you have
bounce,
the plasma and
you'd
everything.
fill the universe with matter and
Okay.
radiation. You'd have a period of expansion like we've observed.
Yes.
You'd have a period of accelerated expansion which re-smooths the universe out, preparing it for the next bounce.
Right.
So that by the time you now begin contracting, whatever drives this acceleration now decays, you begin to contract. And eventually when you bounce, it fills the universe again with new matter and radiation, and the process begins again. And it can occur cyclically. So you
Okay.
could have, that's where the cyclic part comes in.
Right.
These bounces could have occurred in many, many times, even an infinite number of times in the past, and could continue an infinite number of times in the future. So that could be the whole story.
Right. Now, so this is an infinite kind of a cycle,
Yes.
but is the cycle the same every time, or could it be different? And would you have the same energy each time? Do you see, to start with?
So the cycles could continue forever, but they would not be the same. Certainly not literally the same. You and I would not be speaking
Right,
a
yeah,
cycle in
okay.
the past. But
I meant the atomic structure.
the
and so
properties,
forth,
yeah, the
right.
details of the physics would be the same. It would seem to an observer as if things are cyclic, although if they were to observe the universe in its entirety, able to see the whole thing, what they would secretly observe is actually the universe is growing in volume every time, every one of these cycles.
Okay.
And they would see there's more black holes and more entropy in the
Okay.
universe. But in order to see that, they would have to see the entire thing. We only get to see a small region of space, and
okay.
to us, within our little region of space,
Local.
our local neighborhood, things look the same. The temperature, density, the properties
Okay,
of elementary
all right.
particles are the same.
Okay.
But as same as they would a cycle ago and a cycle from now.
Okay.
So to us, it seems cyclic, although it's really...
So there are
there's really this-
variations. There could be variations
there is
in
this
that.
growing, there is this overall trend of growth
Okay.
over time.
And one more thing. Now, so you at some point you get to the end, and in endless universe, this contracts. A confusion for me, at least, is that you do have this thing where the energy is so dissipated in this space.
Yes.
And then it is a question of whether it does. So I'm asking, does it dissipate?
Yeah.
And if it does, how does it contract? You had pointed out it's slow, but
Yes, it's slow, and it's a subtle kind of contraction in which it would seem to us, if we were just looking at the concentration of matter, to be more of a stagnation than a contraction.
Okay.
As to say, once the matter and radiation is dissipated, the way gravity interacts with this matter begins to change during this contraction in such a way that we would say, we would hard for us to see that there was a contraction going on. It would just almost look like the universe just expansion slowed to a point that you couldn't see any change, and then suddenly there'd be this burst of matter and radiation that would fill it with matter, with new matter and radiation. It would continue to grow again.
Okay.
So it's more like grow, stagnate is the way you and I might have described it if we were looking just at the matter within it.
Right.
If we were to look at the gravity within it, we'd see in a subtle way there was this contraction, but it would be hard to notice.
you gave a kind of ballpark figure for time on that too, that
Yeah.
the cycles would be
About 1 trillion years or so.
okay. I
Yeah,
guess we
yeah.
won't be around to see it. We won't be
No.
at an vantage point, and we won't be able to get to.
Unless it's
but it
sooner.
but it does match up with the idea of the fading of the universe with the galaxies. Everything sort of all the lights going out all in time.
It's actually
and
pretty
stuff.
early. No, actually there would be still galaxies.
Okay.
Our Milky Way and Andromeda would still be around at that time.
Well, maybe we could see it.
Maybe we couldn't, but great, yeah.
Yeah, somebody would be
Yeah.
around to see that.
Yes.
Okay, so there are advocates for the inflation, it still works, and there are advocates for the cyclic universe, and everybody's saying, and the Planck, the latest map of the universe, which I think you're going to show us, is the evidence for both. Now, which is it? Or can you tell us why it is so difficult that you can't point to one thing and say, there it is, or we can't now?
Well, okay, so actually what's going on in the field is quite interesting, as much about history of science and people as it is about science. It's true that at the moment, I think most astronomers and cosmologists are advocates of the inflationary picture. It's partly because what I told you was the flaw in inflation, this multiverse.
Yeah.
They choose to ignore it. They rather assume that there is no multiverse problem, and I'll assume that there are none of these rare quantum fluctuations, even though I have no justifiable reason to do it. And if you ignore it, then you get some predictions from the theory. They're not the true predictions of the theory, but there's these pseudo predictions of the theory. And those agree well, interestingly enough, with the data we've observed about when we observe the distribution of galaxies and when we observe the cosmic microwave background radiation. So this is, so what we're going to see here is a kind of map. It's an odd kind of map, which is supposed to represent the entire universe around us. So you should imagine, although it's shown in an oval, it's a projection which is wrapping the sky around us. It's the universe which is a huge distance away from us, a sort of surface which is away from us, around 14 billion light years away from us, and which emitted this radiation 14 billion years ago that's been streaming through the universe until collected by our detectors. And our detectors are essentially cameras designed to look at what is the picture of the light that the light reveals about what the universe was like at that time. These are microwaves. So these are comparable to what you have in a microwave oven. And it doesn't seem to reveal very much to the eye at first, but it's like think of it as a baby picture of the universe, in which if you saw a picture of yourself a few instants after conception, it would look rather unimpressive at first.
But people got awfully excited about the original one.
But you know that picture of you at that time would also contain a lot of information.
That's
you just have to learn to dig it out. And the same with this picture. Although it's showing hot spots and cold spots, it may not seem impressive to you. It actually contains a lot of information. The distribution of hot and cold spots is something that the competing theories predict.
Could you give us a little background, if people are not familiar with that, what is the red areas, for instance, exactly?
I'd say in this image, I think it's been set up so that the red is the hotter and the blue is the colder than average. Where the differences in hot and cold are extremely tiny. There are a few tens of 10,000ths of a degree or less in difference in hot and cold.
But to you, to physicists, that's highly significant.
That is a baby picture taken 14 billion years ago, is enough to go from there to explain all the structure we observe today. Just the action of gravity over 14 billion years takes those tiny little differences between hot and cold, and around them matter condenses to form all the structure we observe. And we know that in very fine detail. So this is a picture which any theory that you would want to propose about the universe would have to match up to. It's a challenge for any theory to match up to it. And the inflationary theory, if you ignore the multiverse problem, just say I'm going to blind myself to it, and I'll just do this calculation, agrees with it, this data up to this point. And that was the result that the Planck satellite team announced about a month ago. A few weeks, I guess more like a few weeks ago. And, but it also turns out that the predictions of the cyclic model are an equally good agreement. So up to this point with the data gathered from Planck. So we could have observed something that eliminated both models. We could have observed something that would have favored one model clearly over another, but at this point the story is they're still tied. But the next year or so we'll see a lot of new measurements, further measurements, not just from the Planck team, but from other teams trying to measure the microwave background by different techniques, which could break this tie.
So do you imagine that the inflation problems, the issues there, that people will come round to looking at that more objectively, or do you see what I mean, with or without that?
I think it's already beginning to happen. I think what happened in the history of the field is that the theory was developed in its early years before we understood there was this multiverse problem. The astronomers then ran off to try, and observers went off to try to prove what were thought to be the predictions of the theory. In the meantime, the theorists discovered there were these problems, and you produced this multiverse, and everyone hoped that problem would go away, and that maybe the theorists, given time, will figure out a way around it. Now we're 30 years later, and well, the data agrees, with those naive predictions, but we haven't found a way to cure the problem. In fact, the data, I say, agrees with it. It actually agrees with only special models of inflation, which introduce some yet additional challenges to the theory that we didn't have before the data. So it agrees and pushes it, but pushes it only if you push it in a tight corner where there's yet other uncomfortable problems about the theory besides the multiverse.
Okay.
So that's the story at the moment.
All right. So we stay tuned.
Stay
in other
tuned.
words,
It's evolving,
but I
and
should point out to the
marches
audience,
on,
you've been ahead of the curve by decades on a number of things. So really stay tuned here. I think. Right, you're hoping to be. Yes, that you will be the lucky one on that. Before we leave this one, I would like to ask, because the word multiverse comes up a lot, right? Yes. And so I wonder if people mean different things by that.
One is the multiverse idea, where you're really thinking about this inflation producing separate patches of space, bubbles or patches of space which are connected by more space.
There you are.
And that's something which is very physical. You should think of it as very physical and real if this theory were true, although it leads to this non-predictability. The other idea that people have is an interpretation of quantum mechanics called the many worlds hypothesis. Yes. So it sounds very similar, multiverse and many worlds, but it has a very different notion. It's the idea that at every single moment when quantum physics says there's a certain probability of X or a probability of Y, that rather than chance choosing X or Y, you actually get both. The world splits into two worlds, one in which X happens, one of which in which Y happens. And the splitting is happening every instant of time, all the time. It's a completely different, and these worlds do not talk to one another.
Right.
It's a very
they don't
different,
talk to each other. There we are.
It's a very different kind of thing.
Exactly, and since it's also theoretical, it really is a difficult thing to keep track of for unless you're in that
it has
field.
no predictive. It has no novel predictive consequences. It's an interpretation of quantum mechanics as opposed to the multiverse, which does have a consequence, namely it destroys the predictability of the inflationary theory.
I see.
So
predictability, yes. Okay, so that is a problem.
That's a problem. That's a serious problem.
Okay. I'm going to leave that now and shift, okay? I'm going to shift over to the quasicrystal, totally different thing here. But this is really fascinating, and I'm not sure whether people are familiar with it at all, but we're going to find out a lot about it. This is an adventure in addition to a fantastic theory and then a discovery and all of that.
So I was going to remind you of the basics. So crystals are forms of matter that you've seen them in stores, and we know they're attractive. I don't see you wearing one on your hand, but you could be. And what attracts us about them are those nice, beautiful, flat facets that we see that are very attractive to the eye. Like a diamond
or something.
Yeah, diamond, sapphire, and rubies.
Ice.
In fact, all matter, all forms of matter that we've known up until the 1980s, if cooled under appropriate conditions, likes to form crystals. And what crystals are forms of matter in which you have a certain arrangement of atoms. It could be a single atom, a group of atoms, or a large cluster of atoms that simply repeats in space to fill space, just like building blocks in a child's toy. So that means the structure of a crystal is very simple. If you tell me how the atoms are arranged in one building block, and I know how to put the blocks together, I get the entire structure. So they all have the property that they are, in which there's a certain cluster of atoms that regularly repeats. And that's called, by scientists, periodic. They repeat with a certain regular period. And then you can ask yourself, how many different ways are there of making periodic arrangements of things? Well, the answer is it's rather restricted. There's only certain symmetries which are possible. This was a very important fact about matter and nature that was discovered 200 years ago that led eventually to the atomic hypothesis. The idea that matter was made of atoms was stimulated by the fact that crystals can only come in certain forms, and those agree mathematically with the ways you can periodically arrange building blocks of different shapes. So this problem is very much like the question in 2 dimensions. If I wanted to tile my shower, what shapes can I use to tile my shower floor? Let's suppose I insist that I use a single shape. What shapes can I use? Well, you could imagine making it with square tiles like that, and we've all seen.
That's where most people are.
That's what most people do. But you may want to do something more interesting, and you might say, what's the most interesting thing I can do with a single tile shape? So you scratch your head and say, okay, I could have used rectangles. I could have used triangles. I could have used hexagons like bees use for honeycombs. If you think harder, you could even think of using parallelograms and rhombi. And you might think at this point the list can go on, but actually that's the end of the list. Try to do it with any other shape. Try to do it with a pentagon. Disaster for your shower. You don't want to do it. It's going to lead to these embarrassing
everybody
floods.
Stay away from that.
Stay away from pentagons. Stay away from heptagons, 7-fold, octagons, 10-fold, 147-fold. So think about that. The only shapes you can use to fill space reduced to 5 possibilities.
Yeah.
So humans love to fill walls, rugs, domes, surfaces, textiles. All up until 1970s, the only patterns that you probably ever experienced in your life reduced to one of those 5 possibilities because it was forced by the mathematics. If you want to make a crystal, you have the same issue in 3 dimensions. You're trying to stack things. So along any one direction, only those 5 possibilities. But I can, because it's 3-dimensional, I could have one symmetry along one direction, another symmetry along another direction. So I could put together different combinations. But it turns out that only takes you from 5 to 14. Only 14 possibilities for all crystals, and we thought for all matter. And it used to be up until the 1980s that the most famous forbidden shape you could make was this shape here, the shape of what's called an icosahedron. Super forbidden because it doesn't just have one 5-fold symmetry axis, it has 6 of them. It has the same symmetry as a soccer ball. So if you think about a soccer ball, it has those pentagons. They come in opposite pairs. And if you rotate the soccer ball by 1/5 of a circle, you get back to the same shape. So that's a 5-fold symmetry axis, and it has 6 independent sets of them. It's the same symmetry. And it was thought for 200 years that was a form of matter that you would never, ever see because you can't stack atoms in a regular way with that symmetry. But in 1984, that is just what Dan Shechtman and his colleagues at the National Bureau of Standards found. They found this material, a mixture of aluminum and manganese, which they had made accidentally in the laboratory, which when they studied it using a process called electron diffraction, revealed a pattern, a special pattern of spots, which tells us that this material has exactly this forbidden symmetry, the symmetry of the soccer ball, the symmetry of the icosahedron. They couldn't explain it. They had no idea how this was possible, but that's what they were observing. Now, as it turned out, my student, Dov Levine, and I had been hypothesizing theoretically about a possibility of a new form of matter which would do just this. And we call these things quasicrystals. In order to violate the 200-year-old theorems of mathematics, we had to relax one of the conditions that makes a crystal a crystal. So our idea was, instead of imagining a matter made of a single building block which just repeats with one period, imagine that you have 2 kinds of building blocks which repeat with 2 different periods, where the ratio of the periods is an irrational number. Can't be expressible as a ratio of integers, like a disharmony. If it were sound, we'd call it disharmonic rather than harmonic. Then what we discovered is if you allow this possibility, you could still have something which is perfectly predictable, very well ordered, because it just involves these 2 periods, but you no longer have the symmetry restriction. So you could have 5-fold symmetry in 2 dimensions, or the super forbidden icosahedral symmetry in 3 dimensions.
Now, were you just playing around mathematically to come up with something like this? I can relax this and tweak that, or did it come from was there any source that kind of inspired it, or you were just goofing off?
Well, it's a kind of the way theorists goof off when they're trying to do work. But I'd originally come to the idea of trying to make this icosahedral symmetry because we had observed if you cool liquids rapidly, let's say if it's a liquid, let's say of a metals, let's say, the atoms like to form locally arrangements which are like the soccer ball arrangement. Now, as you get more and more atoms together, it seemed like they, because of this crystal rule, that they could not figure out how to extend the symmetry, so they would eventually crystallize. But locally, it seemed that they preferred this symmetry to any crystal symmetry.
Okay.
So it just got to ask the question, well, exactly why is it disallowed to make something icosahedral? We knew the mathematical theorem said that you weren't allowed to do it, but theorems are always based on some assumptions.
Right,
so then you
okay.
begin to scratch your head and say, okay, what's the assumption that's forcing this conclusion? And it was the periodicity. We said, what's the simplest thing we could do that would be very predictable, but would violate the assumption? And the answer is to imagine two periodicities rather than, or two repeating elements rather than a single repeating element. And around this time, we encountered something that had been discovered about 10 years earlier by Sir Roger Penrose, and it's a tiling pattern, which is known as a Penrose pattern. I'm showing of it here. And if you look at this pattern, when Penrose developed it, he didn't know anything about quasi-periodicity. He was just trying to make something non-periodic, something non-crystalline, and something where the units could only form something non-crystalline. Now, if you look at the pattern, if it's the first time you're looking at it, it disturbs the eye. Are you looking at something ordered? Are you looking at something disordered?
It's not just the colors.
It's not just the colors. No, the colors are badly chosen colors. It's that your eye can't interpret it.
Yes.
Is it predictable or not predictable?
Yeah, right.
And you can't tell at first. But what Dove and I found was that if you label the tiles with these little line segments, and then you imagine that you see on the right, and then you put them back together again, those little line segments form straight lines that go through the entire structure. Now, when you see that, that's an aha moment, because that says there is a predictability to the structure. The fact that those little line segments line up, you know, before you can't see that they were ordered, but now you can see they are. That's telling you there is order to it, but what kind of order? For that, you have to study the patterns of lines. And they're not random lines. They're quite special lines. If you look at any one set of lines, it's the same as all the others. So in each of the other directions. So that means this really has a five-fold symmetry to it, which, as you know, is disallowed, forbidden.
Yeah.
Then you say, well, how is that possible?
But that it exists.
Yeah, how does it exist?
Yeah.
When you look at the lines in any one direction, you see there's not just one spacing, there's not random, there's just two spacings. So it's something special. And then when you look at the patterns of the sequence of spacings, you discover it's not random. There's longs and shorts, and it goes, well, if you follow it here with long, short, long, short, long. It doesn't settle into any regular repeating pattern. Study it more closely, you discover the ratio of the longs to the shorts follows a ratio of Fibonacci numbers, which in the infinite limit approaches an irrational number.
There you are.
Yeah. So that is a classic example of a quasi-periodic sequence. So that meant the secret to Penrose's tiling, which he didn't even know about, was this quasi-periodicity.
Right.
Now, once you know that quasi-periodicity can give me fivefold, what other symmetries can it give me? That was the next question. Well, the answer was anything. All the ones that were forbidden, an infinite number of symmetries that you thought were forbidden, are now allowed.
Okay, so this just turned everything completely upside down. It must have been a delicious moment.
Oh, yeah, it's fantastic. So here's one with 7-fold symmetry, or 11-fold symmetry, or 17-fold symmetry. So you just dial the number, and you can make a pattern of that symmetry that no human has ever seen before.
Yes.
And there's an infinite, for each symmetry, there's an infinite variety. So you really can choose one that no human has ever seen before quite easily.
And that's really amazing. Now, with Shechtman in his lab, my understanding is that that was truly weird because you had to have like conditions
He was taking very special mixtures, and he was actually, his job at the time was simply to try many different mixtures. He wasn't looking for a quasicrystal. His job was to take all mixtures of aluminum plus X and figure out what crystal forms they corresponded to.
And so he was shocked when he saw
this. And he ran into
this.
something which didn't conform to any crystal form. In fact, he ran into something which actually corresponds to this structure, analogous to this structure, which is the three-dimensional icosahedral symmetry. So now we're going to the third dimension. Now, in this example, and I brought some toys here to demonstrate it, the units now break up and can be, the whole structure is now made, in this case,
everybody will go home
of 4
and do
different
this
units.
Tonight. Yes, this is our homework.
Yeah, 4 different shapes. They're actually all closely related to one another. A geometer would recognize these shapes. They're famous. This one, for example, is a projection of a 6-dimensional hypercube into 3 dimensions.
I won't forget that
as
for
you
a
can all
moment.
imagine, right? But the more interesting thing about them is you notice that their faces are not all the same.
Yes.
That means they can only fit together certain ways.
Okay.
And other ways are disallowed. Well, that's important because when Penrose discovered his tiling, he didn't just make the tiling. He made rules that would constrain the way they were allowed to fit together, so they could only fit together to make that tiling.
Okay.
Why is that important? Well, because if you want to think about atoms forming this structure, you would like to find, the question we were asking is, are there conditions under which atoms would prefer to form this rather than a crystal? And this is a kind of abstract demonstration that if the atomic forces are analogous to these rules, it would force that structure to be the lowest energy state. And this would make quasicrystals not just a possibility, but for some forms of matter, preferred possibility.
Yes, right.
So in 3 dimensions, what Dov and I did was show that we could do the same thing in 3 dimensions that Penrose had done in 2 dimensions. It's more complicated, but you could do it.
Right.
And so when if you were to begin to, if I were to give you a room full of these tiles and say put them together, but you're not allowed to have any gaps, you would discover after some effort, yeah, you could do it, and you'd begin to develop.
How long did it take you to do that?
More than I want to say.
That's a big relief.
Right. But here's an example of when you begin to build a surface here of what it would look like, and you could build it out infinitely in the plane. In fact, it has this kind of corrugated or crinkly surface on it. And then once you built out one such layer, well, you could then start to build the next layer on top of that. So I've begun to build out the second layer here, and it would fit something like that. And then, of course, nothing to stop you from building out the 3rd layer. And here's a beginning. I've done the 3rd layer, and you could build something like that. And you could fill
go
the entire
on forever.
Right. And if atoms had these interactions, this is the configuration they'd want to form. And it would have 6 different axes of 5-fold symmetry, super forbidden, like Shechtman's material. And when we computed the electron diffraction pattern, the same thing that Shechtman had computed for had measured for his sample, we had computed that already for this structure.
Okay.
And when his paper, when a friend brought a copy of his preprint of his paper to my office, and we flipped and we saw the pattern, we just about hit the roof. Because on my desk was this pattern, and we could see immediately recognize what he was doing. So that's how the subject began. That's how the subject.
So you were the one who came up with the
this was the
term
theory.
quasi.
So then the term quasicrystal became associated with Shechtman's material. There was debate for a number of years whether, well, I should say, it didn't happen immediately because there was some debate about whether Shechtman's material really was quasicrystal or not.
I did realize that, yeah.
Because if you measured, so the way you tell what the material is by scattering electrons or X-rays off of it, and his X-ray and electron patterns were not perfect. His spots, you get spots, but they weren't quite sharp spots. They weren't quite in the right positions, and so that opened the door to, that opened the question of, is it because these are just, been poorly made, or is it impossible for them to ever reach the ideal state that you'd expect? And what settled the issue was the discovery of yet other quasicrystals. We don't really know if Shechtman's material is quite delicate and not stable. It tends to crystallize if you heat it too long. So you can't get rid of its defects before it crystallizes.
All right.
But then people began to discover other quasicrystals.
Is this synthetic? Again,
all synthetic.
Able doing
so
them
just
in the
playing in the
lab
laboratory,
so
people began, once they had that example, they tried to see if they could make something that would be stable. And here was the first one which didn't transform to crystal, and it was made in Japan by a group in Japan, on Pansai in Japan. And it was the first, I call bona fide quasicrystal with truly sharp spots, dead on to what the theory would have predicted. And now we knew quasicrystals were possible. We knew the structure isn't just conceivably possible, but exists.
So we started out, you've worked it out theoretically, it should, there.
Well, it may or may not.
It came up sort of in the lab, and he got a Nobel for that, as perfect as it was. But then the next thing was you got interested, I'm going to find one, right? So would you tell us that wonderful story?
Sure. So first of all, why were we interested in the question? Well, even though we now knew that the real thing can be made in the laboratory, it still wasn't settled as to why it forms. Is it because it's energetically stable, like this model would tend to lead you to believe? Or does it only because you formed it under very special conditions in the laboratory? Because all the laboratory examples, you know, follow a very careful protocol in order to make a very good quasicrystal, like the example you're seeing there. Whereas our theoretical view, my theoretical view had been that what this model shows is there should exist examples of atoms that actually prefer to form that. And just like in nature, we don't have to work hard to make a crystal, nature does it for us. Maybe nature makes a quasicrystal for us. So that opened up the search for, opened the question of, could we find a natural quasicrystal?
Did other people feel, did other physicists feel, well, it must be out there somewhere too, or were you
oh, they thought it was completely nuts to ask that question.
There you are. That's what I mean.
Right.
That's because that would fit the pattern of being ahead of the curve. But at the time, it was called zany to be thinking like that. Can you? What is?
Well, zany both because it seemed unlikely. Maybe theoretically, people's prejudice was you had to form them under special conditions. But how would you have found them? Why wouldn't humans have found them before? If they'd been studying minerals for thousands of years. But I guess by this point, my prejudice was always question people's assumptions and see what you can do.
Yes.
By this point, we did it. So, around 1999 is when the search began, and what I had developed by that point was with a student was a mathematical algorithm for looking at computer databases of diffraction data and identifying minerals which contain diffraction data from many minerals and identifying from that likely suspects for quasicrystals, things that kind of close, you know, maybe we should go back and look at that sample and check. And so we began years and years of finding those samples and checking and discovering failure and finding a sample, discovering failure.
How many years did that go on before you went out? And
it was 3 solid years of, you know, steady work and then slow work of, you know, it gets slower after a time, mainly because finding the minerals itself is a challenge.
So you had to put out a kind of bulletin, please send some examples.
If you were lucky, if you were lucky, yeah. Usually it meant you had to find where this, you know, there was some sample in the catalog in this computer database. You had to figure out, look it up, where it came from, find the person who entered it. See if the person's still alive, do they still have the sample. It was an adventure. Each one was an adventure. But it was a complete failure. It was a failure, mainly because the computer catalog wasn't precise enough for our job. But we didn't stop. It gave us a lot of false positives, so we didn't stop. But in the meantime, we put out a call, official call, saying, anyone wants to help join us, please do. But no one answered this call until in 2007, when this fellow named Luca Bindi, who lives in Florence, he's the head of the Department of Mineralogy in Florence, volunteered, emailed out of the blue, never heard of him before, didn't know his museum, volunteered to join our effort. It turned out to be a great stroke of luck, both because of what he had in his museum, but also because he turns out he's a wonderful person who became as fanatical about this subject as I was. So by this point, you know, other people had left.
You had to be fanatical.
You had to be completely nutty, off the wall, fanatical to pursue this issue. So again, we experienced with him the same sort of failure for the first 2 years, and then he pointed out that he had some things in his museum that were not in our catalog, and we should check some of those. And what he brought to our attention was this material, which came in this little box. It's labeled Quasicrystals.
That hard word to say, yes.
Yeah. It says it comes from, the box said it came from Khatirka, which is a river in far eastern Russia. And most of what you're seeing there in the box is just a piece of plastiline. The plastiline is to hold the rock, which is at the very tip of it.
So, right. Now I see the image on the top, the little angular piece on the top.
And if we blow it up, it looks like that. So now it looks gigantic. But you have to imagine the whole big deal here is going to be something about that size. And it's a complex rock, all kinds of things going on in there. You can see there's many minerals in there. It's not a nugget or something like that. But among the material, when we sliced it and diced it, was material which, when again we checked our mathematical algorithm, scored pretty well. So it was shipped to Princeton, and brought to our laboratory, where we then had a chance to do a proper diffraction study of it. And I didn't bring the diffraction pattern. And out front came the diffraction pattern, which agreed beautifully with what you would get for a
what a
quasicrystal.
moment.
It was, yeah, it was quite a moment.
Champagne corks all over the place.
This was around 6 a.m. on January 1st, New Year's Day, 2009. So the champagne had already been popped. And we hadn't expected to see anything. This was just an attempt to try to check it out and see if we could eliminate it. But it wasn't just a good quasicrystal pattern. It was a magnificently perfect one, as much more perfect than Shechtman's original one, as perfect as any I had seen of any material, the best materials. And furthermore, when we measured the composition of it, it turned out to be 63% aluminum, 24% copper, and 13% iron. And you didn't jump out of your chair when you saw that.
No,
because
yes, right.
means nothing to you.
Right.
But to someone who works on quasicrystals, this would be famous.
Yeah,
because this is the same composition as that guy.
Okay, so this is the signature.
Yeah.
Absolutely.
So it was not just a quasicrystal, it was the same composition as the synthetic guy. So now we knew exactly what we had in our hands. But we knew that this guy had been made under very careful laboratory conditions, whereas our guy had been made in the middle of this complex rock. So although we thought the story was done, this was just the beginning. Because the question now is raised, how did nature manage to do that?
Okay.
How did nature manage to make something when nature doesn't control things in this complicated rock? And that's what started us on the really wild chase.
Now, I need to point out to the audience, because we're beginning to run out of time, but that this is an adventure that is out of this world. So you can ask about it in the QA and get a better idea of it. I'm waiting for the movie because it is very much worthy. It is amazing. But where did you go to find this thing?
The trail, just to give the audience a little thing, was to try to essentially reduce to a detective story to figure out how did this rock get to this museum. And it was a very long detective story. It took about 1.5 years to track down where it had come from. It involved things like finding a missing collector in Amsterdam, finding that he had secret diaries, looking for mysterious Romanian smugglers, KGB agents, the story is smugglers, gold mining operations, all kinds of strange things. So it's a long story, torturous story, at the end of which, remarkably, we actually found ourselves talking to the person who in 1979 had picked this rock out of the ground.
Amazing.
Yeah.
This is like more than the needle in the haystack.
Oh yeah, way beyond.
Unbelievable.
Yeah. And so many twists and turns and dead ends and disinformation. And so the full story is really.
It is amazing.
It has so many pieces and so many things we learned from it. But we eventually found our way to talking to this fellow, who was the fellow in '79 actually pulled it out of the ground. And here is actually his first email to me explaining the history of how he was sent to this obscure stream.
It's really obscure. Yeah.
Just a tiny little stream where gold had been found, and he was sent to look for platinum. He was sent by the head of the Institute of Platinum in Soviet times to look for platinum there. He had failed. He had dug through this very strange blue clay and failed, but he had found these little rocks which were shiny, had some shiny components to them. He thought he'd just bring them back to his boss to show he had done something. He didn't want to end up in prison, the Gulag or something like that. So that's the last he had heard of them until we had contacted him. He didn't know that this fellow had taken them back, discovered new crystal phases in them, smuggled the material out, and it found its way to Florence, and that we had found a quasicrystal in it. But he knew about the quasicrystal story because that had recently been announced in Russia, that we had found a quasicrystal that was supposed to have been found in Russia. He suddenly discovered he was connected to the story.
That is something.
So then he decided to join us in
your amazing expedition.
Right.
Yes.
So in the meantime, work in the laboratory revealed that our material was definitely natural. Not just natural, but a piece of a meteorite that formed in the early solar system. Not just early, but actually at the very beginning of the solar system. It was a piece of a meteorite that was 4.5 billion years old. So not just a little older than Sheckman's material, but 4.5 billion years old.
That's so amazing, because how much of that stuff falls into your hands.
That's
you know what I mean? That's, you know, that's amazing.
And the meteorite experts on our team had long ago told us that the one thing our material couldn't be is a meteorite. And now, from the data we had gathered, they agreed it was a meteorite, but it was now a very, very interesting meteorite, because it came from it was one of the first meteorites to form in our solar system, and now it had all these new phases of matter in it that were thought to be physically impossible to have formed in nature.
What an amazing thing. So I have to ask, then, is that this seems to take extraordinary conditions, both in the lab, but in nature. So if we picked up a meteorite that's more recent, we wouldn't see this.
Probably
so
not.
What would the conditions be that would cause this kind of
Well, that was the
formation?
question that everyone had. So and we wanted to do more tests, but there was no material to test. It had all been used up in the work up to this point. So the only way you were going to find more was to actually travel to Chukotka, this place in far eastern Russia. This is the very far east corner of Russia, the part that's just opposite Alaska, to try to look for the material. So, but to go there is impossible, because it requires special permissions from the government, from the FSB, from the local government, etc. So it was and you have to get people willing to go. But even though it's impossible, we actually did manage to go. And this is the team that we brought, which is a combination of Russians, Americans, and Italians. Luca's there in the middle. Valery is near the right with the white hair, is the one who had originally picked the material out of the ground. My son, who's a geophysics graduate student, is in the group. There's a cat sitting in the front, Buck's the cat. So that's, we had our team, and we went, and we had to travel across the tundra for 4 days in order to get to this obscure stream in the middle of nowhere. And just to give you some impression of what that is like, this is what life was like for 4 days I'm glad you brought this picture. Yes. This is what a vehicle. Yeah, there were 2 of these vehicles, one stranger than the next. And every stream crossing, and there were many, many, many stream crossings, was like this. And always unpredictable, because you don't know if you're going to break something on the way down. You can see you're falling a distance in a heavy vehicle. Here's an example where we were driving, and most of the time there would be like a kind of trail ahead of us, but here there was no trail. And I turned to Victor, our driver, and I said, well, where's the trail? And he gave me a look. He didn't speak English. There it is. Trail? Who needs a trail? So it makes trails. It makes it seem like the vehicles are invulnerable, but they're not. Probably the scariest moment for me was when we had to cross the Khatirka River. You don't know, it's permafrost region, so you don't know how deep the rivers are. Yes, I'm sure. So were we going to make it, or weren't we going to make it? The vehicles were supposed to float, but they've never been tested. Convinced. They've never been tested under these conditions. So this is what the thing was like, and we did have, we broke an axle. The motor had to be put together several times, going and coming. Wow. We had a near fire. We almost got stuck several times. And did you find it? So you collect the material. You collected about 1.5 tons of material out of the ground. You pan it. And then you pan it. And look for this little teeny weeny. But you can't know the answer when you're in the field. You just have to gather. You can't know the answer until you manage to bring the material back. We searched for 6 weeks, and we found more samples. Amazing. Yeah. In fact, we've now found 9 samples from the collection. That's fabulous. But it's all from this meteorite stuff. All from the same meteorite. So it can't, it's just not going to grow in your backyard tomorrow. I don't think so. I don't think so. Okay. And we're still trying to understand from that material what it's telling us about the odd sequence of events that occurred in the very beginning of the solar system that allowed quasicrystals and these other odd phases of matter to form. Yeah. What a thing to put your signature on. It's amazing. It's a wild story. It is. And I do hope they're going to make a film of this. It's out of this world. We are out of time, I am sorry to say. I'd like the audience to be able to ask their questions a bit, but that was delightful, and I do thank you very much. Thank you. And let's get some questions.
as much as I'd love to ask about quasicrystals in our limited time,
Yes.
since I'm trying to wrap my mind around some aspects of cosmology,
Yeah.
could you just comment on your cyclic model, how it differs, and maybe the answer is completely, from earlier, more rudimentary cyclic models that I had read about maybe 30, 40 years ago, wherein it was sort of like the universe, did it even, in terms of its expansion, could it even have the expansion speed to escape, to overcome its escape velocity, or was it just going to collapse back on itself, sort of a very rudimentary yo-yo thing? Are there any common threads between your model and that more?
So what you're talking about, I sometimes call it's sometimes called an oscillatory model, or you think of it as a breathing model, where the universe expands and then contracts and expands and contracts. Those kinds of oscillatory models that people were thinking about in the 20s and 30s broke down, failed, because what happens is during each expansion stage, when you produce stars and galaxies, there are certain irreversible processes that take place that increase the entropy of the universe, and then when it collapses again, it reconcentrates that entropy, so that which causes the next bounce to be bigger than the next, and the next bounce to be bigger still. So instead of it's cycling the way you were hoping it would, so it would cycle forever to the past and the future, going forward in time, the cycles got longer. Going backwards in time, they got shorter, and they got short very fast, and you ended up with a beginning again. So it was not extensible as a cycle in terms of solving this beginning of time problem. So we have found in our construction a different kind of cyclic model. You might call it pseudo-cyclic. It appears to be cyclic in the sense that the thermometer, the temperature, will seem to read the same from cycle to cycle. The density, the entropy density, will seem to be the same from cycle to cycle. But it's producing more volume each cycle as well as more entropy. And what that does is it allows the temperature and density to keep coming back to the same values while you're producing more and more stuff, more and more volume. So if you like, locally, a local neighborhood, it seems like things are the same as before, even though globally you're actually having more and more stuff from cycle to cycle. That gets around the old problem of not being able to keep the cycles going. And so it brings back conceptually the idea you were looking for, getting rid of the beginning of time problem, but gets rid of the entropy problem that one had for the old breathing type oscillatory models.
Thank you.
I'm really loved your presentation. And I have a question about the quasicrystals. Any natural crystal has a process of nucleation and growth, just how it's formed, and one infers that that's true of quasicrystals as well, whether in the lab or in a meteorite. I guess my question, though, is in any real phase change situation, you're going to have multiple sites of nucleation, and as those sites grow, you get domain boundaries that don't align properly. In a quasicrystal, where you're depending on this irrational ratio, it seems you'd be even more prone to imperfections and defects where something starts to nucleate in a certain way but gets a wrong signal, and there's a defect. And so I guess I'm just wondering, how can you even tell that something is a quasicrystal that would have to repeat, non-repeat forever, versus, or how big are these actually accurate domains before it runs into another one, whether in the lab or in the meteorite? Or just could you comment on that whole
That's an excellent question. It was exactly that question that plagued the field in its early days after Shechtman. When Shechtman's data did not conform so well with the quasicrystal picture in detail, one of the issues was exactly the thing you raised. How are the atoms to figure out to grow anything of any size, any reasonable size, that wouldn't exactly repeat the way a crystal does? How does it manage to do that without creating lots and lots of defects? People also had the experience that if you gave them, if I gave you a pile of Penrose tiles with his rules, and I said, fill this table, you'd have a heck of a time doing it, because you'd find that as you began to put them together, you'd make mistakes, you'd have to undo them, and you'd have to keep repeating this process. Wouldn't atoms have the same problem, which is, again, the question you're asking? And that held the field up for a few years. But it turned out that that impression, based on the Penrose tilings and Penrose's rules, are wrong. A team of us, including myself, showed that by using a different set of rules, you could make sure that any time you added a tile, you'd never make a mistake, and you could continue that ad infinitum. Same for the structure you're seeing before you. So that in principle, there was no mathematical blockade as long as the atoms obeyed the right rules. Then, around the same time, the example I showed you of this quasicrystal, which is bona fide, was found. Sure enough, that one is like single domain quasicrystal with spots right on. So, and it's well, I remember that particular example, but it can be grown to the scale of millimeters, so comparable to crystals. So although we thought there was a fundamental problem, we were just wrong. Quasicrystals, at least for certain symmetries, can grow perfectly to large sizes.
I guess as a follow-up question to this gentleman's question here, when you see multiple periodicities with these crystals, do you have an increase in, the error of the data looking, for, I don't know whether you'd be doing single crystal analysis with the electron diffraction, or whether you'd be looking at, a more complex crystal structure, or looking at the order, and how do you kind of tease apart these effects? I mean, there's enough problems with the field using single crystals with one periodicity. Mm-hmm. Like, how do you even begin to tease out all of that with, 2 or 3 or, heavens God, more than that,
You mean, how do you figure out that it's there? How do you determine it's there?
I mean, it kind of almost borders on his question.
So in terms of making the materials, you need some luck. You need to search through many different kinds of materials to see something that will make what you're looking for. In terms of identifying it in the laboratory, once you've made it, that is straightforward. When you shine electrons through a crystal, it produces a very distinctive pattern of sharp spots with a certain spacing between them, a kind of lattice of spots. For quasicrystals, it turns out you also get sharp spots, just like for a crystal, but they have it's a kind of snowflake pattern in which between every pair of spots, there's yet more spots and yet more spots, a kind of fractal pattern. That's a characteristic of something which is 2 periodicities which are irrational. And it's very easy to recognize, very striking. I was going to do a laser demonstration, and maybe we can do it after the show. I can do it against the wall or something like that so you can get an idea of what I'm talking about. But you can immediately recognize it. And so when we found the natural quasicrystal, it's like an instant to realize what we were looking at. Because it's such a characteristically different pattern than any crystal pattern would give.
Yeah, hi.
Hi.
Is there a connection between the concept of pi and the expansion and contraction of the universe?
Pi, you mean the number pi?
Yeah.
Not particularly. Do you have something in mind? I don't. Maybe I'm missing a question.
It's a never-ending number.
It's a transcendental number. Not that we know of. No. It's different kind of. I think it's a different kind of infinity than. Sorry.
In your cyclic universe on the rebound, is it the universe itself that contracts and then rebounds, or does space also contract and rebound?
Well, when you're talking about expansion and contraction, we're always talking about the space.
Space itself.
Yeah. Now, space can contract, but in order to tell that it's contracting, you need to have stuff in it that you can recognize as coming closer together or farther apart. And what will happen in the contraction in our cyclic universe is that during this period of contraction, there won't be the stuff that you need to follow it. So you will have trouble recognizing the contraction when it's happening. It'll seem to you more like a stagnation. If you were actually looking at particles, it would seem more like they're stagnate rather than contracting. And then suddenly there'd be this burst of matter and radiation that would tell you that you've now bounced. So it's a kind of subtle kind of contraction that's happening in this model, which is different from just the simple breathing in and out that we were talking about before.
Space itself is big, contracting, expanding.
Yes.
Space itself.
Yeah.
What is beyond?
Well, as far as we know, in general relativity, you don't need to ask the question of what's beyond. The space can expand and contract without there being a beyond. It can, for example, imagine an infinite rubber sheet, and then you stretch it and you draw graph lines on it like graph paper, like a ruling, and then I stretch it so each square is twice as big in every linear dimension as before. What's it expanding into? It was infinite before, it was infinite after, but it's clearly stretching. Things are spreading out. Space can be like that. It could just be infinite and stretching into nothing, just stretching. It's stretching. There's more of it.
It's stretching rather than expanding, you're saying?
Yeah, stretching is a better word, I think, than expanding. I mean, the Big Bang model should really be called the Big Stretch model, because that's what it really is. It isn't unusual. I mean, it's unusual that the Big Bang model was not named by the inventors of the model. It was invented by Sir Fred Hoyle, who hated the model. And he particularly wanted to give it an insulting name. But that name is stuck and forever caused us to have to explain to students that the Big Bang is not an explosion, it's a stretching. And that's the way.
Fred Hoyle?
Sir Fred Hoyle, yeah.
Enemy of the whole thing. I'm sorry, I'm afraid we're running out of time. I'm getting nasty signals back there.
Okay.
We'll have to wrap it up, but I think while we're cleaning up and stuff, if you have some questions, please go right ahead. Thank you very, very much.
Thanks, Yvonne.
Thank you so much for joining us. It was really a pleasure. It was really great. Thank you.